Greetings, students. My name is Malcolm Burns, and I'm an instructor in the first year medical course. You're actually going to see me on the very first day of classes on Wednesday, July the 14th. And my goal today is to give you sort of a review of acid-base chemistry and include some medically relevant information regarding acid-base and osmotic balance and imbalance. So you'll be required to view this lecture before coming to class. So again, this is an acid-base review. And what I'm going to be doing is writing on this piece of paper, and it's being captured here and saved using Zoom. And then I'll have this recording somehow posted to Blackboard. But let's start by talking about water, because all of the properties of acids and bases ultimately depend on the properties of water. Okay, so what is water? It's a small polar molecule. It has a bent molecular shape, okay, with two pairs of two pairs of unshared electrons on the oxygen, a partial positive charge between the two hydrogen atoms, partial negative. So it has this dipole moment, and the bond angle is around 104 degrees. It's bent. And this molecular structure gives water some unusual properties. It has a very high boiling point, for example, and can form ice, which is critically important for life on Earth. And ice is less dense than liquid water, which is important for lakes not freezing in the winter, for example. But it engages in hydrogen bonding with other molecules of itself and other molecules. So it engages in hydrogen bonding, okay, with itself and other molecules, okay, in solution. It can diffuse across membranes, albeit slowly. And actually, there's a class of protein channels that allow water to flow through them. They're called aquaporins. And aquaporins are located in different places, but one place they are found is in the nephron of the kidney, where they can allow water to enter and be reabsorbed from the lumen of the nephron of the kidney. So they're water channels, water channel proteins. Okay. Now, so again, all of the properties of acids and bases and of osmotically active species ultimately depend on the properties of water, and we're going to see some of that later. Right now, I want to talk about osmotic activity. It's a colligative property. Which means that it depends on the number of particles, of osmotically active particles in solution. You may remember from general chemistry that there are other colligative properties like boiling point elevation, freezing point depression. And then you can raise the boiling point of water by including some osmotically active species like salts. And that's actually the basis of, using salt on highways in the winter, is that it depresses the freezing point so that the roads may not freeze as readily in the winter. Another term, osmolarity, is a measure of the concentration of osmotically active species in solution. And I want to talk about the term 1 osmolar solution. A 1 osmolar solution, okay, contains 1 milliosmol of osmotically active particles, okay, per liter of solution. A related term is osmolality, which is just, instead of per liter, it's per kilogram of solvent. And of course, as a solution for very dilute solutions, these two are about the same, because the mass of water, molecular mass of water, is just a kilogram weighs, so the density of water, right, is 1 gram per milliliter. And when there's nothing dissolved in water, it means that a liter of water is 1 kilogram of water. Okay? But when you have things dissolved, and the more things you have dissolved in water, the more that deviates, so that a liter will weigh more than a kilogram. And so these two values, the osmolarity and the osmolality, will begin to become different, but for very dilute solutions, they're kind of the same. Okay. So another term I want to bring up, besides osmolality and osmolarity, is isotonic saline. Okay, this is found in IV drips. Okay, and it contains concentration of sodium chloride that's 0.154 normal, okay, which is the same as 0.9% weight per volume of sodium chloride, okay, and an isotonic saline solution has the same osmotic activity as a 0.308 molar solution of sucrose. Okay, and so now, you wouldn't want to use sucrose in an IV drip because bacteria might start to grow there. So you use something that's inert, like sodium chloride, to provide the needed osmotic activity. But that gives you an idea of what isotonic saline is. Okay. Now, the osmotic activity of blood plasma depends mainly on the concentration of certain ions, sodium chloride and bicarbonate. okay, sodium chloride, and bicarbonate. Okay, these ions are the so-called anion gap ions. And we're going to talk about the anion gap and how a broadening of the gap can be indicative of a certain kind of acid-base imbalance. But the osmotic activity of blood plasma depends mainly on these ions because these are the main ions that are present. But it also is also affected by the concentrations of glucose and blood urea nitrogen. So the concentration of glucose and the concentration of blood urea nitrogen. Okay, and so we can come up with a formula. Okay, where the concentration, the osmotic activity in milliosmoles per liter, okay, is equal to 2 times the concentration of sodium ions, okay, plus the concentration of glucose in the blood, okay, divided by 18, okay, plus the concentration of blood urea nitrogen divided by 2.8, okay, whereby these concentrations of glucose and blood urea nitrogen are in units of milligrams per deciliter. And that's why we divided by 18 and 2.8. The molecular mass of glucose is 180. And the molecular mass of molecular nitrogen, N2, is 28. But since we have units of volume of deciliters instead of liters, right, we need to divide by a number that's tenfold smaller. So 18 instead of 180, 2.8 instead of 28. And why are the values in units of milligrams per deciliter? Because those are the clinical values. That's how it's expressed clinically. And my guess is that these sodium ions here, 2 times the sodium ion concentration, reflects the concentration of, sodium along with the counter ion that's present. So we're sort of augmenting that value from the main ions that are present with concentrations of glucose and blood urea nitrogen that can affect overall the osmotic activity of blood plasma. All right, so now I'd like to display a couple of slides that are also available on Blackboard under miscellaneous, files. And so sometimes it's a little hard to read, so you can access those files from Blackboard to follow along. But here I wanted to talk about pH and osmotic activity in the blood and other fluids in the body, and how they're maintained within a narrow range, especially pH. So, the pH of fluids in the body is affected by what we take in our diets, and is controlled both at the respiratory system through ventilation of CO2, and at the kidney and the renal system by the excretion of acid or base, the retention of base in particular, at the kidney. And osmotic activity, osmolarity, is of course affected by this intake of salt and water, and is controlled through sweating, okay, and in the urinary system as well through the excretion of salt, retention of water there. Now, let's look at the physiological limits of pH. pH is maintained in blood plasma in a narrow range between 7.35 and 7.45. It's around 7.4, which corresponds to a hydrogen ion concentration of 40 nanomolar. Now, when pH drops, something called acidemia can result, which can cause organ dysfunction. And if the pH drops too much, it can cause coma or death. So, for example, a pH of 6.8 would be considered far too low. That's a concentration of hydrogen ions of 160 nanomolar, and death or coma could result there. And then if pH rises too much, alkalemia can result. You can have organ dysfunction. And if it goes too high, say to 7.8, which corresponds to a hydrogen ion concentration of 15 nanomolar, then you can have coma or death. So you see what a high pH means a low hydrogen ion concentration. A low pH means a high hydrogen ion concentration. And that's because pH is the negative log of hydrogen ion concentration. So there's an inverse relationship there. And the other thing to keep in mind is that the pH scale is kind of compressed in the sense that a small change in pH indicates a large change in hydrogen ion concentrations. So for example, if you have only a 0.3 pH unit change, that corresponds to a twofold change, a doubling of the hydrogen ion concentration. So 0.3 means doubling. So it's good to keep that in mind as well, and sort of thinking about changes in pH. Small change, again, in pH could mean a large change in hydrogen ion concentration. Now let's look at the pH values of some different bodily fluids. Blood plasma, 7.4. Interstitial fluid, which is the fluid between cells and tissues, 7.4. Inside the cell, inside a liver cell, it's around 6.9. But inside a red blood cell, it's 7.2, which is actually a little bit more acidic than blood plasma. So inside the red blood cell, it's slightly more acidic. Inside the lysosome, which is an organelle in the cell, it's more acidic, quite acidic, and that's because of the special role that the lysosome has in degrading macromolecules, where the enzymes that work there require that lower pH to work. Gastric juice, very acidic. Pancreatic, basic, somewhat basic. Human milk has the same pH as plasma. Urine, pH can vary according to how much acid is being secreted there at the kidney. And when you lose fluid from either the stomach or the intestine through vomiting or diarrhea, that could cause pH and osmotic imbalance with the loss of those fluids. And then the body has to try to readjust. Here's another slide. It's a little bit hard to make out. So again, you might want to depend on those slides from that I've given you on Blackboard. But we can look at the chief chemical constituents of cells, and this figure shows 3 different pairs of bar graphs that show the levels of cations and anions, which are osmotically active, in different kinds of fluids. So blood plasma on the left, in the middle, interstitial fluid, the fluid between cells and outside of cells, and on the right, the fluid, if you will, inside of cells, so the cytosol. And there's some things you can notice. For example, inside of cells, we have high levels of potassium, magnesium, phosphate, and this is a monohydrogen phosphate shown here, which is one of the species that exists around pH 7.4, and then quite a few, and protein. So the anions are mainly potassium and magnesium inside cells, and the anions are, phosphate and protein. So interstitial fluid is turns out, is very similar in composition to blood plasma, in the sense that there's a lot of sodium, okay, outside of cells and in blood plasma, not as much potassium. And there's a lot of chloride outside of cells there. But here's a key difference, and that is that in blood plasma, we have soluble proteins that contribute to the osmolarity, whereas in interstitial fluid, we don't. The proteins tend to be tied up in structures. They're not free in solution, so they're not osmotically active. So this is pretty flat. There's almost nothing here. Whereas there's quite a bit of protein in blood plasma that's soluble. The other thing to notice, so you see here, the levels of cations and anions are equal. You're going to have equal amounts of each of those two. There are also some non-electrolytes, right, that contribute to the osmolarity of these fluids. These are molecules that can engage in hydrogen bonding, but they're not charged, right? So they wouldn't move in an electric field or support an electric current like an electrolyte would. But here's one thing you can notice, and that is if we look inside of cells and outside of cells, we see that inside there's a lot of potassium, not much sodium. But outside of cells, there's a lot of sodium and not much potassium. And that's because there's an active pumping of sodium out and potassium in to cells by means of what's called the sodium potassium ATPase or pump. So there's an actual ATP dependent pump that pumps those ions either in or out, and there's a gradient of each of those ions that's maintained across the cell membrane, and actually that gradient drives important processes through and fuels what's called secondary active transport of other species across the membrane. But there are pumps for not only sodium and potassium, but also for chloride and for calcium, so that chloride is pumped out. You don't see much chloride here inside of cells, just a little bit. There's a lot more outside of cells, so it's pumped out. And then calcium, we see what? A little bit, some calcium outside of cells, right? Virtually none inside of cells. It's not that there isn't any calcium inside of cells. It's that it is sequestered in internal structures. For example, in muscle cells, the calcium is sequestered inside of what's known as the sarcoplasmic reticulum. And then there can be a release of internal stores of calcium during muscle contraction. And that calcium will actually stimulate enzymes that are involved in the breakdown of glycogen for energy in muscle. So anyway, this is some of the constituents that are present. So now let's talk a little bit more about osmolarity. Okay. Okay. So let's continue. Okay. And I want to emphasize or mention that there are two hormones, okay, that help regulate osmolarity. And those are ADH, anti-diuretic hormone, also known as vasopressin, and aldosterone. So let's talk about those two. First, anti-diuretic hormone, also known as ADH, also known as vasopressin. And there are different kinds of vasopressin. A common one has an arginine on its amino terminus, and so it's called arginine vasopressin, or AVP, arginine vasopressin. So what is it? What is ADH? It's a peptide hormone. Peptide hormone is produced by the hypothalamus and stored in the posterior pituitary. by the posterior pituitary, from which it is released when needed, and it acts at the kidney. Okay, what it does is it stimulates the movement of aquaporins to the epithelial cells that line the nephron of the kidney. Movement of those aquaporins to the membrane that faces the lumen of the nephron. Simulates movement of aquaporins. Okay, and those aquaporins now can allow water to flow into those epithelial cells lining the lumen of the nephron. And so what then are these, what is the important role? Okay, and so the important role of AVP is that it's important in water retention at the kidney. Water retention, retention of water. Okay, so we could well imagine then what would happen if we had excess AVP being produced Okay, so excess. What happens there? Okay, we have hyponatremia, Hypo and atremia, hyponatremia, which means too low sodium in the blood, in the body, right? Because what's happening here is that we are bringing in too much water and that's diluting the sodium. Okay. Now, if we have too little AVP, on the other hand, of course, conversely, this will cause hypernatremia. Right? We're not bringing in enough water, and the sodium is at too high levels, and the body will respond. There will be a sensation of thirst, known as polydipsia. That word means excessive thirst. Okay, and there will also be a phenomenon called polyuria, which means excessive urine volume. Too much urine, a lot of urine. Okay, and that's in response to the high levels of salt in the body. So the body, you're going to feel thirsty, you're going to drink water, you're going to eliminate that salt through the urine, so you'll have excessive urine volume, right? So that's the what happens when you have a deficiency in AVP, and so it will cause then what's known as diabetes insipidus. Okay, so too little AVP will cause something known as diabetes insipidus. Okay, again, too low levels of AVP. Okay, again, polyuria, polydipsia. However, but blood glucose levels are normal. You know, this polydipsia, polyuria is also are also symptoms of what's called diabetes mellitus, in which you have too high levels of glucose in the blood. Glucose is also osmotically active, And so when you have too high levels in the blood, that has the same or similar effects, right, as having too much salt from having too little AVP. So on the surface, right, or at least what's the right word? Trivially, they resemble each other, but their causes are very different. In the case of insipidus, it's caused by there being too low levels of AVP. In the case of diabetes, there's either a lack of production of insulin at the source or cells not being able to respond properly to insulin. Okay, so now there are different kinds of diabetes insipidus. One is called central diabetes insipidus. Okay, and this means that there's not enough AVP secreted. Okay, by the hypothalamus. There's also a kind called nephrogenic. Okay, where the cause is at the nephron of the kidney, nephrogenic diabetes insipidus. And there's some insensitivity now at the nephron itself. Right, so we can think of two different kinds. All right, now let's talk about the other hormone, which is aldosterone. Aldosterone. Aldosterone is a steroid hormone, okay, and it's produced by the adrenal glands. Okay, here it's involved in sodium retention by the kidney. Sodium retention. Now, I'll tell you right now that obviously there's a connection or a similarity with AVP because, if you retain sodium, too much sodium, then you're going to have hypernatremia. If you retain too little, you're going to have hypo. And so you have all the attendant effects there. Now, another interesting thing is that this hormone is indirectly involved in acid-base balance. In controlling acid-base balance. I'm going to explain that in just a minute. So let's look at so you can have insufficient levels of aldosterone. Okay, so let's say insufficient levels of aldosterone. This causes what's known as Addison's disease. Addison's disease. And of course, you're going to have hyponatremia. Okay. But what you're also going to have is metabolic acidosis. Okay. And that's because there's a sodium hydrogen exchanger at the distal tubular epithelium. A sodium hydrogen exchanger, okay, at the distal, okay, tubular epithelium. Okay, so what this exchanger does is to exchange sodium for hydrogen ions sodium moves into the cells and hydrogen moves out. So let's say you're not moving enough sodium in, okay? You're not retaining enough sodium, okay? So what's going to happen there is that you're also not going to move enough hydrogen out. And so that hydrogen will be retained by those epithelium cells. And so you're going to have acidosis. And it's called metabolic because it occurs at the kidney as opposed to the lung. This is something we're going to discuss in more detail later. What is metabolic acidosis, for example? Okay. Now, another disease is called CONS, CONN'(S). So when you have too much or over secretion of aldosterone, okay, you've got now too high levels in the body, in the blood, and this will cause hypernatremia, and the opposite of what happened with too low levels. You'll have metabolic alkalosis. Okay. Now, so with both of these hormones, what we see is an effect on the osmotic activity of the blood. And just in general, you have too high osmotic activity. This will cause what's known as osmotic diuresis. Okay, which results in dehydration because water is being eliminated in the urine, and you're drinking. You want to drink more water to replace that. And actually, this can have a dietary origin with too high or elevated salt intake, right? Or it can have an origin in having too high blood sugar level, which is what you would have in diabetes mellitus. Okay. All right. So this is just sort of an introduction to osmotic activity, maintaining osmotic balance, and it's something about pH and the importance of maintaining pH in a certain narrow range in the body and in the blood plasma in particular. What I want to do now is switch and talk about acids and bases. And so I want to give a review of acid-base chemistry. Okay, review. And this is going to be basically what you've had in general chemistry in college. But I'm going to add on some more biochemically relevant information. So let's first look at some definitions. Okay, what's an acid? A really basic thing here. What is an acid? An acid, according to the Bronsted-Lowry definition, is a proton donor. It can donate protons to water, forming what's known as a hydronium ion. And a base is just a proton acceptor. It can accept a proton from water, generating a hydroxide ion. Okay. And we could talk about strong and weak acids and bases. So let's look at some examples of strong acids and bases. Okay. What these do in solution is they ionize almost completely. Ionize completely, okay? That equilibrium for their ionization lies far to the right. And here's some examples. Okay, so hydrochloric acid, sulfuric acid, right? Nitric, HNO3. These are all strong acids, and some examples of strong bases would include sodium hydroxide, potassium hydroxide. Okay. One thing about these acids is that they're all molecular, although when they are placed in solution, they break apart. Whereas sodium hydroxide and potassium hydroxide are ionic compounds, but they also, when they dissolve, form ions. Right. So, what about weak acids? And bases. Okay, these ionize incompletely. Excuse me, in solution. And equilibrium is involved. An equilibrium. So with strong acids and bases, the equilibrium lies so far to the right that we don't even need to bother with, talking about them. But for weak, we need to talk about equilibrium. And we'll get to that soon. So some examples of weak acids are the ammonium ion, okay? Phosphoric acid, believe it or not. Carbonic acid, okay? And their conjugate bases, ammonia, okay? Dihydrogen phosphate ion, the bicarbonate ion. These are all bases, right? So here we have weak acids listed here, and their conjugate bases, which are weak bases. And so we can talk about what are known as conjugate acid-base pairs. So ammonia, ammonium, dihydrogen phosphate ion, phosphoric acid, bicarbonate, carbonic acid. Those are conjugate acid-base pairs. Yeah. One thing I want to emphasize is that all of the acid-base properties of aqueous solutions arise ultimately from the autoionization of water. All acid-base properties arise ultimately from what's known as the autoionization of water. Okay? Water actually can undergo what's known as autoionization, where an individual water molecule splits apart to form a hydrogen ion and a hydroxide ion. Both of these are dissolved in water, and actually this is a simplistic way of writing it, because this hydrogen ion is actually attached to a water. And actually, I could write it as two waters forming a hydronium ion, H3O plus, and an OH minus. But this is sort of a simplified way of writing it. Now, you can think of this as liquid water. We can also write, and there's an equilibrium constant called the autoionization constant, okay, called K sub W, and K sub W, by the way, is actually very, very small, it's 1 times 10 to the minus 14 molar squared. It's the equilibrium constant for this autoionization, okay? And we can write what's known as the ion product constant expression as well, where K sub W is equal to the concentration of hydrogen ions times the concentration of hydroxide ions. Now, when you normally write an equilibrium constant and an equilibrium constant expression, you divide the concentrations of the products over the concentration of the reactant. Each species raised to the power of its coefficient, which in this case is 1 for each. But notice I only have these two terms here instead of water being on the bottom. And that's because the concentration of water in water is constant. It's very high and constant at around 55 molar. So we can think of it as a constant and simply incorporate it into K sub W and ignore it in this equation. All right, so again, this is called the ion product constant expression. And concentration of water, as I just said, in water is equal to approximately 55 molar. It's not gonna change. It's a very large and very high. Okay. Another important equation you need to know is the definition of pH. pH is equal to the negative log of the hydrogen ion concentration. And so we could talk about pH as the minus log of the hydrogen ion concentration, and actually pOH, which is the negative log of the hydroxide ion concentration. And for the ion product constant expression, where K sub W is equal to, H plus concentration times OH minus concentration, we can take the negative log of both sides of that equation. And then the ion product expression, ion product constant expression equation becomes pKW is equal to pH plus pOH, where I took the negative log of both sides of that equation. That's kind of written awkwardly. Ion product constant expression, when we take the negative log of both sides, becomes this. All right. So what is the pKW? I'm sorry, the negative log of KW is just 14. So 14 is equal to pH plus pOH. And what this means, practically speaking, is that if you know the pOH of a solution, you can find the pH, because the pH is equal to 14 minus pOH. Now, I'm saying this because we're going to be using that later, so I just wanted to introduce this now. Okay. All right. So now I want to talk about strong acids and bases for a while. Okay. So these contain a hydrogen or hydroxide ion, whether it's an acid or a base, plus some neutral counter ion. Okay. And the counterion could be, it could be chloride for, say, hydrochloric acid, or it could be in sodium for sodium hydroxide. So again, H plus and a neutral counterion such as chloride, OH minus and a neutral counterion such as sodium, Na plus. And pKa, which are the negative log of the Ka, the acid dissociation constant, values range from a range, or that said that wrong. These pKa values for strong acids and bases are far from physiological pH. Right. And so what is pKa? Just what you would expect. It's a negative log of the Ka value. And the Ka is the acid dissociation constant. And let me talk about what that is more. So again, for strong acids and bases, for strong acids, right? Strong acids, in particular, the pKa values are far from physiological pH. Okay, so that's what pKa is. It's the negative log of the Ka. So let's imagine an acid. Okay. So an acid is called HA. Okay, can ionize to form H plus and A minus. And there's an equilibrium constant, K sub A, for the dissociation of the acid. It's called the acid dissociation constant. And Ka is equal to the concentration of hydrogen ions times the concentration of A minus ions over the concentration of HA at equilibrium, in the equilibrium mixture. Okay. And for strong acids, okay, for strong acids, this HA pretty much ionizes completely. So that happens, this lies far to the right. So i.e. equilibrium lies far to the right. Okay, what does that mean? What does that mean? Ka is very large. And if Ka is very large, therefore, pKa is very small, okay? So this Ka here is very large. Okay, so, and the pKa, which is the minus log of that, is very small, okay? Because the pKa of a very large number will be small, and I'm sorry, the negative log of a very large number will be small, and the negative log of a very small number will be large. So that's good to keep in mind there. The pK is very small, and it's much less than 7.4, which is the physiological pH. All right, so I want to look now at the titration of a strong acid. Titration of a strong acid. So for example, let's work a little problem here. Let's look at the titration of 100 milliliters of a 0.1 normal solution of hydrochloric acid, okay? And by the way, that would constitute 10 milliequivalents of that acid with a solution of sodium hydroxide of the same concentration, 0.1 normal sodium hydroxide. So this is a strong, we're titrating a strong acid with a strong base. So what does the titration curve look like? Let's figure it out. Okay. So as we titrate, what's going to happen to the pH? Okay, as we add hydroxide ions, and let's look at the number of milliequivalents of hydroxide that's added. Okay, we're going to start here. pH is going to rise quickly through the equivalence point and then level off. Okay, and so we can look at different points on this titration curve. Let's look at the equivalence point. Okay. And let's look at the initial starting point. Let's call that A. Let's look at the midpoint of the titration called B, the equivalence point called C, and then let's look at one other point here, which is let's call it D, and that's going to be when we've titrated 90%. Okay. Now, if we have 10 milliequivalents of HCl, we're going to require 10 milliequivalents of the base to titrate it completely. What happens is that the acid that's present reacts with the base that's added, right, to form a salt, NaCl, plus H2O. Acid plus base gives salt plus water. So we're going to need 10 milliequivalents to completely titrate the 10 milliequivalents of the acid, and we're going to need 9 to titrate 90% of the acid. We know that already. Okay. But let's unpack this. Let's look at each one of these points here, A, B, C, and D. So let's look at point A first. Okay. And let's sort of make a little table. So we're going to start with 10 milliequivalents of the acid. Okay. At the beginning of the titration, we're not adding any sodium hydroxide. So we're going to keep that acid. We're not going to form any sodium chloride or any extra water. Fine, no problem there. Now let's look at point B. At point B, we're going to add 5, right? 5 milliequivalents of the base. And it's going to react with 5 of the 10, leaving 5 milliequivalents of acid still there. All the base is going to react up with the acid, the 5 milliequivalents of the acid. We're going to form a 5 of sodium chloride and 5 of water, but that 5 is not much different from 55, so we're just going to say 55 molar. At point C, that's the equivalence point. Okay, we have reacted and used up all the acid with the base added, and we're going to have 10 milliequivalents of NaCl, and again about 55 molar water. Actually, it's 55 here too at the top, right? And then finally, at point D, we'll add 9 milliequivalents, add 90 milliliters of the sodium hydroxide solution, which corresponds to 9 milliequivalents. So we'll have 1 of the acid left, and we'll have 9 milliequivalents of salt and 55 molar water. So this is kind of a little table, and based on this table, using this table, we can ask some questions and do some calculations. So let's ask this question. What is the pH at points A, B, C, and D? A, B, C, and D. So let's calculate that. Start with point A. So At point A, what do we have? All we have is the hydrochloric acid. Okay, and we know that hydrochloric acid, when it gets in solution, is just going to ionize completely. And so we want to know, what is the concentration of hydrogen ions? Well, it's the same as the concentration of the acid, 0.1 normal. So the hydrogen ion concentration, right, is 0.1 normal, or you could consider it to be 0.1 molar here. And therefore, the pH, which is the negative log, right, the hydrogen ion concentration, is just negative log of 0.01 or 10 to the minus 1 molar, which is just 1. So the pH of that acid solution is just 1. Now, let's look at point B. And just to remember what point B is, we're at the midpoint of that titration. We've titrated half the acid. Okay. So at point B, we have 5 milliequivalents. So the hydrogen ion concentration is just the same as, right, the concentration of HCl that remains, which is 5 milliequivalents divided by the volume. So that's equal to 5 milliequivalents of H plus divided by now 100 plus the 50 we added of the sodium hydroxide solution. So it's 150 milliliters, which is just 0.033 normal, or you could consider it to be molar, same thing there. And so what's the pH? pH is the negative log of 0.033, which is just, if you take the negative log of that, you get 1.48. Okay, so good so far. Hasn't risen very much. It went from pH 1 to pH 1.48 at the midpoint. Now let's look at point C. Now, let's think about point C. Okay, at point C here, all we have is salt, sodium chloride, which is a neutral salt, doesn't affect the pH of the solution. And so the pH is just 7, okay, the pH of water, because that sodium chloride is not going to affect the pH at all. pH equals 7.0. And then finally, point D. Okay. Now, again, hydrogen concentration is equal to the hydrochloric acid solution, hydrochloric acid concentration, which is 1 milliequivalent per what divided by whatever the volume is. It's equal to 1 milliequivalent divided by the 100 milliliters plus the 90 of sodium hydroxide we added. So that's what? 0.0053 normal or molar. And so the pH then is equal to the negative log of 0.0053 normal. It's just equal to 2.28. That was at point D when we titrated 90%. So let's think about that a minute. What do we have there? What do we have there? Let's quickly look at sort of a little inset here. And let's look at pH versus milliequivalents of hydroxide added. And what do we have? Okay. We have something that doesn't change very much and then rises quickly. Okay, so at point A, it's 1.0 pH. Okay, so the different points, point A, right? Point B, C, and then D was here. So what happens? pH goes from 1 to 1.48 to 2.28, and then to 7. Okay, so what we see is that you know, the pH rises slowly, even up to 90% titration, and then jumps rapidly. So this is 100% titration. That was 90. 1.48 was 50% titration. And at the beginning, of course, we had no titration at all. So there's a very rapid jump, and that's characteristic of a strong acid where the pH curve rises dramatically and steeply. Okay, that's not going to be true for weak acids and bases. So, all right, we've talked about strong acids. Let's talk about weak now. Let's talk about weak. Weak acids and bases, they ionize incompletely, less than 10%. Weak acids and bases. Again, ionize incompletely. Let me check something here. All right, good. Now, let's consider a weak acid. Let's look at an example. Okay, acetic acid. Acetic acid. It has the formula CH3, the structure CH3C double bond O, OH. That's acetic acid. And sometimes we can call it HOAC, okay, for short. It's this proton right here that's lost. And when it's lost, it gives an acetate ion, acetate, which we can call OAC minus. So this is what acetate looks like. Right? Acetate ion. That's the conjugate base of acetic acid. So here's the equation for the dissociation of acetic acid in solution. So the AQ just means that it's dissolved in solution. Yeah. And we can write an acid dissociation constant expression, which says so it's an equilibrium case of A that governs that equilibrium constant that governs that equilibrium. In the larger case of A, as the more it will tend to ionize, the smaller the less. So Ka, which is the acid dissociation constant, is equal to the concentration of hydrogen ions times the concentration of acetate ions divided by the concentration of acetic acid at equilibrium. And that has a value of 1.74 times 10 to the minus 5 molar, which is quite small, which means that it doesn't really ionize very much. And so we're going to work a partial problem here, partial problem. To see how you would set up a problem, how you would calculate the pH of a weak acid solution, or solution of a weak acid. So let's consider acetic acid, okay, ionizing in solution here to form H plus ions and acetate ions. And let's consider some situation. Let's say we have a 0.01 molar solution of acetic acid, HOAC. Let's calculate the pH of this solution, okay? And I'm not going to do the whole calculation, but sort of set it up, okay? So initially, you can imagine some hypothetical initial situation where we have 0.01 molar concentration of acetic acid, and let's say hypothetically it hasn't yet ionized. But then, boom, let's say it ionizes. Let's look at the final situation. What we have now is 0.01 minus X molar concentration of acid, and we have X amount of H plus and X amount of acetate. Okay, we can calculate the pH. What we have to do is calculate the concentration of hydrogen ions, determine that, and that will allow us to calculate the pH. And so what we have to use is that acid dissociation constant expression, okay, which says K sub A is equal to, now plugging in the values of X, X squared, okay, divided by 0.01 minus X. That's so what we have to do is figure out how to solve this equation. Now, if we didn't simplify it, we'd have to use a quadratic equation, but luckily for us, we can, because the value of K sub A is so small here, and that's typically true for weak acids, you can ignore it. You can ignore it. You can cancel it in this equation. Ignore X because it's negligible, because the value of K sub A is so small that not much is going to ionize, and so it's small relative to 0.01. Right? So then that means that K sub A is equal to, excuse me, X squared over 0.01. And that means that X, which is the hydrogen ion concentration now, is equal to the square root of K sub A times 0.01 molar. So all you have to do is take the square root of K sub A times 0.01, and that will give you the hydrogen ion concentration, and then take the negative log of that, and that will be the pH. Okay, so that's how you would calculate the pH of a weak acid. And we're going to do an actual calculation in a minute when we look at the titration of a weak acid. But let's talk about now a weak base. Let's look at a weak base, and let's look at particular here ammonia. Ammonia is a weak base. So what happens though when you put ammonia in water? Okay. Ammonia reacts with the water, H2O, but it's a weak base, so it doesn't react completely, and we form an ammonium ion, which is in solution, and a hydroxide ion as well. So what the ammonia has done as a weak base is pull a proton off of water to give an ammonium ion and hydroxide ion. Now there's a base dissociation constant called K sub B for this, and K sub B is going to be equal to the concentration of ammonium ion, okay, times the concentration of OH minus, divided by the concentration of ammonia at equilibrium. Okay, and it turns out the K sub B for ammonia is equal to 1.78 times 10 to the minus fifth molar. That's also very, very small. And so the same guidelines we applied there can be applied here. So for a 0.1 molar solution, okay, of ammonia, right, we can calculate the pH. What is it? It would be, well, first we have to find what's called the pOH. And this is where that what I told you earlier comes into play. We have to find the hydroxide ion concentration, take the negative log of that, and then subtract that from 14 to get the pH. So the strategy, right, is going to be find OH minus, or calculate OH minus concentration, right? Then calculate POH, and then from that calculate pH, and that's what we want to get. What is the pH? So you know, we can plug in values of X. Here we have X amount of ammonium ion, X amount of OH minus, 0.01 minus X amount of ammonia, and so we'd have K sub B is equal to X squared divided by 0.01 minus X, right? And then we can ignore the X there, and so we have X, solving for X, which is equal to the hydroxide ion concentration, is equal to the square root of K sub B times 0.01. And so again, once you find OH minus, then you find the negative log of that, and then you subtract that from 14 to get pH. So that's how you would find the pH of a solution of a weak base. All right, now I want to introduce another term, buffer. What is a buffer? A buffer is, it's a solution that can resist changes in pH when small amounts of acid or base are added to it, okay? So it's able to resist changes in pH when small amounts of acid or base are added to it, okay? It typically contains, or it does contain, a weak acid and its conjugate base. Weak acid and its conjugate base, or it can be a weak base and its conjugate acid. In significant and approximately equal amounts. So if you have a weak acid and its conjugate base in fairly high and equal amounts, then you will have a buffer. So I want to talk about a particular buffer briefly, and that is the bicarbonate buffer that's present in blood plasma. Again, blood plasma. Okay. Bicarbonate buffer is present in blood plasma. So, so what's going on there? There's an equilibrium that's involved and is the backbone of that buffer. And that is the equilibrium for the ionization of carbonic acid. Carbonic acid in solution can ionize to form a proton, which is also in solution, and bicarbonate ion in solution, okay? There's a particular pKa, a Ka, and a pKa. The pKa for this ionization is approximately 6.0, approximately 6.0. Now, this is an example. When you have a decent amount of carbonic acid, the weak acid, and bicarbonate, its conjugate base, when you have, again, significant and about equal amounts, here's what happens. So first, you can add a small amount of an acid. When you do that, when you add the acid, it reacts with bicarbonate, forming carbonic acid. And so the equilibrium will shift a bit to accommodate that disturbance. That's called Le Chatelier's principle, okay? But if you add a small amount of base now, that will react with the carbonic acid, and the equilibrium will shift in the other direction to accommodate that change, that disturbance. And so what happens is that there's not much change in pH. And I want to illustrate that with an equation called the Henderson-Hasselbalch equation. Henderson-Hasselbalch, Hasselbalch equation. It's derived from the acid dissociation constant expression, in which you take the pH of both, the negative log of both sides and rearrange it. And what you end up with is pH is equal to pKa plus the log of A minus over HA. And that's for a weak acid, HA, ionizing to form H plus and A minus with a Ka governing that equilibrium, right? That's what we're using here to write the Henderson-Hasselbalch equation. But specifically though, for the bicarbonate buffer, it looks like this. pH is equal to 6.0, because that's the pKa, plus the log, right, of the concentration of bicarbonate over the concentration of carbonic acid. All right, and this is a ratio. You can call this the ratio, if you will, okay, the ratio. And here's the thing, is that so if you add a little bit of acid, sure, this bicarbonate level goes down a little bit, right? The carbonic acid goes up a little bit. But since there's significant amounts and about equal amounts of these two, the weak acid and its conjugate base, then this ratio is not going to change very much. And if the ratio doesn't change, guess what? The pH doesn't change much either. So that's how buffers help maintain the pH of a solution. And I want you to notice a bit here how the pH is related to the ratio, how the pH is related to the ratio of the conjugate base to the weak acid. Okay, so let's make a little table here. Let's look at the ratio, and let's look at the pH. Okay, so if the ratio is, say, 1 to 100 or 0.01, let's say it's 0.01, right? Then the log of 0.01 is negative -2. It's -2. So let me say that again. If the ratio is 1 to 100, this is 0.01 or 10 to the -2, and the log of that is -2. And so the pH is equal to the pKa, which is 6 in this case, -2. But I want to write something that's generic, right? So let's say, though, that the ratio is 1 to 10 now, 1 to 10. So you have 0.1, and that's 10 to the -1. And so the log of that is -1. So the pH will be the pKa -1, 6 in this case, right? Let's say you have a ratio of 1.0, equal amounts of these two. The log of 1 is 0. So when you have equal amounts of the conjugate base and its weak acid, the pH is just equal to the pKa value itself, okay? And then extending that, when it's 10, then you have the pH of pKa +1, and when it's 100, the pH is pKa +2. So that's some sort of general guidelines there that we can look at, And one thing to point out here is that at the midpoint of a titration of a weak acid, when you have equal amounts of conjugate base and weak acid, because you've titrated half the acid, the pH is equal to the pKa. Okay, so and that's also where you have the best buffering capacity. So to put it this way, a buffer, okay, forms at the midpoint in the titration of a weak acid. Right, in that case, we have pH equals pKa. So we're going to take a look at that because we're now going to look at the titration of a weak acid, and then we're going to close out this session by looking at some amino acids, titration of some amino acids. So let's do a little problem now. Let's look at the titration of acetic acid. A certain concentration of acetic acid with sodium hydroxide. Okay, so let's do this little problem here. Okay, titration of acetic acid. Let's look at 0.01 molar solution and 100 milliliters of it, okay, with 0.1 molar, same concentration or normal, sodium hydroxide, okay, solution. And bear in mind that the Ka for acetic acid is 1.74 times 10 to the minus fifth mole. All right. So here we have, it's what are we going to do here? We've got a burette. Okay, it's sort of a crude diagram showing a burette with sodium hydroxide in it. Okay, and a crude diagram of a beaker here with our acetic acid. We have 100 milliliters of 0.01 molar acetic acid. Okay, we've got here our 0.01 normal or molar sodium hydroxide solution. And we're going to add this into the, going to titrate this weak acid. And this is actually, there's an electrode in here and it's connected to a pH meter, okay? And we can see, you know, how the pH changes as we add the base to the acid solution. And actually, we can draw a diagram, a graph, showing how the pH will change as we add different millimoles of OH minus. And it's going to have this kind of a shape, you know, of any typical titration curve. And we can look at the same points, A, B, C, and D on this curve and calculate the pH at each one of those points, just like we did for the strong acid. So now, so how many millimoles of acid do we have? Well, we have concentration of 0.01 molar, which is the same as millimoles per milliliter, or moles per liter, times 100 milliliters. milliliter units cancel, and we end up with 1.0. So we have 1.0 millimoles of acid. Okay, so when we titrate it, we know, okay, we're going to have added 1.0 millimoles of hydroxide, sodium hydroxide. We also know that at the midpoint, we will have added 0.5. And at point D, it'll be 0.9, right? And of course, at the beginning, it's 0. We know that, so we can say all that. Okay. Now let's look at these different points. Let's calculate the pH, and let's look at point A. Let's calculate the pH at the different points. Okay, let's start with A. So here we have a weak acid. And we already set this problem up before, right? And so we know that the pH is going to be equal to the negative log of the hydrogen ion concentration for the weak acid when it ionizes in solution. And we know also that the hydrogen ion concentration is going to be equal to the Ka times 0.01 molar square root. You know that. And so what is the Ka for acetic acid? We've dealt with this before. We know what it is. It's going to be 1.74 times 10 to the 5 molar times 0.01 molar square root. And we can find that. So, you know, the units are molar squared, and so we take the square root of that. We can have units of just molarity. So it's 4.17 times 10 to the minus 4 molar for the hydrogen ion concentration. And the negative log of that, it's the pH, it's equal to the negative log of 4.17 times 10 to the minus 4 molar, which is just 3.38. So the pH that we start off with for the acetic acid solution by itself is 3.38. Now, let's move on to the second point, point B. What's going on there? It's going to be very easy, very straightforward, right? Because here's what's going on. We've added sodium hydroxide now, okay? And this reaction occurs, and we get, you know, what? Sodium acetate, which is plus water. All right. So we've added 0.5 millimoles of the sodium hydroxide. Right? It reacted up. We're going to have 0.5 millimoles of the acetic acid left. We would have formed 0.5 millimoles of sodium acetate from the reaction, right? And this is about 55, as we know, right? So what do we notice? Equal amounts, right, of acetate and acetic acid. In the Henderson-Hausbach equation, again, that ratio is 1. And so the pH is just equal to the pKa value. That's why at point B, the pH is equal to the pKa, the negative log of the Ka, which is, what is that? 4.76. Okay, so the pH now is 4.76 at point B. So went from 3.38 to 4.76. Now, let's look at point C real quick. So that is the equivalence point. Okay, what's happening there is that the acetic acid is reacting with the sodium hydroxide, okay, to form sodium acetate and water. Okay. We've now used up all the acetic acid with the sodium hydroxide that was added at the equivalence point. And we now have 1 millimole of this sodium acetate. Okay, 55 molar water. So what do we have now? We've got 1 millimole of it right there, okay? So what is the acetate concentration? It's equal to that 1 millimole, right? Divided now by 200 milliliters, because we added 100 milliliters of the sodium hydroxide, which was of the same concentration as the acid, and it reacted, okay? And so what is that? 0.005 molar. Now, what are we going to do with this? Okay, so now we've just got acetate in solution. Okay, no weak acid, just the conjugate base. What is that going to do? Well, it's going to react. It's going to react with water. It's a base, and it's going to pull off a proton to form some acetic acid and an OH minus. Right? That is what's going to cause the solution to be somewhat basic. There's a case of B there. Okay. Now, what is the case of B? What is the case of B? Let me tell you what it is. Turns out that case of W is equal to case of A times case of B. So if we know case of A and case of W, we can find case of B. Case of B is equal to case of W divided by case of A is equal to 10 to the minus 14 molar squared divided by 1.74 times 10 to the minus 5 molar, which is equal to 5.75 times 10 to the negative 10 molar. That's a really small number. Okay, so it's not really going to ionize very much here at all. Okay, but that's sort of a little sidebar calculation of how we determine what the case of B is. Now, to find out what the pH is, what you have to find is the pOH, and to do that, you have to use the base dissociation constant expression. Okay, and we kind of worked this out earlier, so I'm just going to rely on what we did before. We know that the OH minus ion concentration is equal to X in the equation we saw before, and it's equal to K sub B times 0.005 molar square root, right? Because this is the concentration of, all right, that's what that is. That acetate that's present, right, is going to react with water to a very small extent, okay? We want to know how much hydroxide is produced, and this is how you determine it. That's equal to 1.7 times 10 to the minus 6 molar. And so the negative log of that is equal to negative log of 1.7 times 10 to the minus 6, which is equal to 5.77, but that's not the pH, that's the pOH, right? Right. And so therefore, the pH is equal to 14 minus 5.77, which is 8.23. Yes. So, yeah. And just one more calculation, folks, and that is when you've titrated 90% of that acetic acid. What is a pH? Well, the acetate ion concentration, when you've titrated 90%, is 0.9 millimoles of acetate produced, divided by 190 milliliters. And the concentration of acetic acid that's present is just 1 being left. I'm sorry, 0.1, right? 0.1 being left, divided by 190 milliliters. And plugging this into the Henderson-Hasselbalch equation, we can calculate the pH. pH equals pKa plus the log of OAC minus concentration divided by HOAC. Okay, we just plug these values in here. You know, this is right here is OAC minus, right? And this is HOAC. Plug those in there. And really what it is 9 over 1. 9 over 1, because these concentrations, you know, if you plug those in, they'll cancel and you'll end up with a 0.9 over 0.1, or just 9 over 1, or just 9. So the pH then is equal to 4.76, which is the pKa, plus the log of 9, and then gives a value of 5.71. So what's going on here is that if you look at how the pH changes, okay, going from point A to B to C to D, I'm sorry, A, B, D, C, it's going from 3.38 to 4.76 to 5.71 to 8.23. And this jump from, you know, this movement from 5.71 at 90% titrated, right, to 8.23 is not nearly as dramatic. So not as dramatic an increase as for a strong acid, titration of a strong acid. All right, folks, we're getting close, now, so what we've looked at is the titration of, you know, strong acid, weak acid. We've learned some things about acids. And now I want to apply some of that to amino acids. So let's look at the acid-base properties of alpha amino acids. Okay, some of the properties of alpha amino acids. And so I'm jumping the gun a little bit, but later I'm going to talk about amino acids as the building blocks of proteins. And this is the general form that they have. An alpha amino acid will look like this, okay? An amino group, an alpha amino group, an alpha carboxyl group, and it's called the alpha hydrogen, and then a side chain R, which varies from one amino acid to another. And this is sort of the general form of an amino acid. Now, one thing about amino acids is that amino acids are amphoteric. This means that they have properties of both acids and bases. They have both an acidic and a basic group. So let's look at the acidic group. Okay. So here's the amino acid. It's that carboxyl group that is the acidic group. Okay. So what happens is that carboxyl group can lose a proton. It can act as an acid. And when you do that, you get just, you know, carboxylate group now with a minus charge. Okay, of course, it can regain a proton as well. So this is the equilibrium here. But here we see an amino acid acting as an acid. It has an acidic group. It also has a basic group because that amino can gain a proton. Can gain a proton there to form an NH3 plus group. Okay, so the whole point of this is just to illustrate that amino acids are amphoteric. They have properties of acids and bases. They have an acidic group and they have a basic group. All right, so acidic group there, and here's the basic. Acidic and basic. So this first one lies to the right. Okay, and the second one also does, in the sense that the carboxyl group tends to be unprotonated, and the amino group tends to be protonated. Carboxyl group is acidic, and the amino is basic. Right? Now, and what this also means is that at physiological pH, okay, the alpha amino acids, okay, exist as hybrid ions with both a positive and negative charge, known as Zwitter ions, Z-W-I-T-T-E-R, Zwitter ions. It's a German word, just means hybrid ions. And so they look like this. The positive charge there on the amino group and a negative charge on the carboxyl group. That's what they look like. Okay, so let's take a look at some amino acids real quick and start with a simple amino acid, alanine. But first, before I do that, I'm going to show you the titration curve for alanine. But let's just do a quick rundown and just list some different amino acids. Let's look at alanine, okay? And let's look at its different pKa values. So, you know, we can talk, I'm going back to the previous page. We can think about the pKa for the loss of a proton from the carboxyl group, okay? pKa for the loss of a proton from the amino group. And then also on the side chain, there could be an ionizable group, and that's true for some amino acids. Okay. Now, alanine, though, has a simple methyl group on the side chain, which is not ionizable. And so even though it has a pKa for its carboxyl group, which we're going to call pKa1, of 2.34, and a pKa for its amino group, which is 9.69, its side chain is not ionizable. So this pKr is, we don't talk about it having an ionizable group or pKa for any ionizable group on its side chain because its side chain is not ionizable. But now let's look at a couple of others. Let's look at aspartate. Aspartate does have an R group that is looks like this: CH2, CO2H. Okay. CH2, CO2H. And this is ionizable. See this carboxyl group here on the side chain? It can ionize. And so we can write pK values for the alpha carboxyl, which is 1.88, for the alpha amino, which is 9.60, and also for the side chain, which is 3.65. And we can also talk about the amino acid, for example, lysine, okay, which has as its side chain the following: CH2, four methylene groups, and an epsilon amino on the side chain. Well, that's basic. And so the pKa of this side chain is going to be high. It's going to be 10.53. But for the alpha carboxyl, 2.18. The alpha amino, 8.95. And what you can see from this is that the pKa values for the alpha carboxyl and the alpha amino are similar among these amino acids. They're not that different, right, from each other. Here. That's one thing you can see. Now, let's look at the titration curve for alanine. Titration curve. Okay. First, let's consider what happens to alanine when it's titrated. Okay. So we start at a very low pH, very acidic, and you're going to have, here's what alanine looks like. Right? At the beginning of a titration curve, everything is going to be protonated. Okay? And then, and we can actually sort of look at it down here. Let me maybe just do this here. Okay. Here's a titration curve. This is what it's going to look like. Because alanine has two ionizable groups, right? So that means that it has two equivalence points as we titrate the carboxyl and the amino. Okay. Okay. Yes. So here again, this is what we'd have at very low pH when we just start the titration. Okay. At the beginning of the titration, we'd just have this species where everything is protonated. But then as we begin to add hydroxide ions, things are going to happen. And what's going to happen is that the carboxyl group is going to lose protons first. You can also go backwards in the titration. So it look like this. Okay. And then once we've titrated that entire carboxyl group, we'll be here at the first equivalence point. But now, let's now what can happen and what will happen is we'll titrate the next group, which is the alpha amino group. It will begin to lose protons as the pH goes higher and higher. Okay, and so we'll have this. Okay, and so we can look at this. We can look at this, and we can make sense of it. Okay, so first of all, what are the charges? So then we would have reached, by the way, the second equivalence point when we carry out the titration of the amino group, the full titration. So, all right, so this, what do we have here? What do we have? Let's unpack this. What are the charges? So the charge on this first one right here, first species, is just +1. Right? The charge on the middle species, where these two charges balance, is just 0. And then the charge on the third species is -1. So the charge changes as you titrate, right? So this is the first equivalence point. This is equivalence point number 1. We've titrated the carboxyl group. Here's equivalence point number 2. We've completely titrated the amino group. And they've got some other points of interest. Right? This midpoint here is midpoint number 1. Where the pH is just equal to the pKa 1, okay? And then the second midpoint, where, so midpoint, where the pH is just equal to the second pKa 2. Okay? What else? What else? Also, notice that at the first equivalence point, the charge on the species is 0 at the first equivalence point. So how does the charge change? It goes from a +1 at the beginning, right, to 0 at the first equivalence point, to a -1, at the second equivalence point. And at the midpoints, the charges will be +1/2, right, and then -1/2 charge. Because say at the second midpoint here, we're right here, we have equal amounts of these two species, one of which has -1, the other 0, and so the overall average charge is -1/2. Whereas for the first midpoint, it's between +1 and 0, so it's +1/2. Yeah, so we can sort of make sense of all this. Now I want to introduce a term, and that term is called the isoelectric point or pH. The isoelectric pH is the pH at which the species, the amino acid species, has no overall charge. So the question is, what is the pH at this first equivalence point? Because that will be the pH at which the species has no overall charge. Now you can calculate that. It's called the PI value, okay? Isoelectric pH. PI turns out for a simple amino acid like alanine is equal to the average of the pKa's that flank it. So it's going to be pKa 1 plus pKa 2 divided by 2, and it's going to be equal to, looking at that table up here, right, 2.34 and 9.69. So 2.34 plus 9.69 divided by 2 equals 6.01. And that's, again, for alanine. Now, one quick thing I want to say is that you can calculate the PI of any amino acid by doing a similar analysis. I'm going to do that for aspartate in just a minute. But also proteins, which are made up of amino acids, have pKa values, but there you can't calculate it because the protein has a very complex folded structure, and some groups are more exposed than others, and so on. So you have to determine it experimentally. But the PI value for a protein would be the pH at which it no longer migrates in an electric field. So you can keep changing the pH and see where it no longer migrates, and that would be the PI value. Okay. Now let's take a look at the amino acid aspartate and look at its titration curve just real quick. Okay. So what about aspartate? Okay. So let's take a look and see what happens to it when you titrate it. But first, I'm going to tell you this. Here's the table. It's an abbreviated table showing the pKa values for aspartate. 1.88, okay, 9.60, and 3.65. And I'm going to tell you right off the bat that actually to calculate the PI, you would use the first It's the pK1 value and the pKr value. And so therefore, the PI is equal to 1.88 plus 3.65 divided by 2, or in other words, 2.8. And so the question we want to ask is, how did we know this? How do we know this? Okay. And the answer is, let's take a look. So look and see what happens with aspartate when you titrate it. So here's what aspartate looks like. It's got its, alpha carboxyl, alpha amino, and at low pH, they're both protonated. And it's got its side chain, which looks like this. Everything is protonated at low pH at the beginning of a titration. Okay. But now, let's say we're going to start to titrate it, start pulling off protons. The question is, from which group will the proton be pulled off first? And the answer is the one that has the lowest pKa value, so the alpha carboxyl. And by the way, this carboxyl is called the gamma, side chain gamma carboxyl. And so what are we going to do? What are we going to get? That carboxyl with a negative charge, this amino group still charged, having a proton, and the side chain carboxyl still having a proton. Of course, we can go backwards. Now let's remove a second proton. The question is, where is that going to come off? Okay, and the answer is the second carboxyl, because its pK value is the next lowest, side chain carboxyl. So it's going to be CO2 minus, CH, CH2, CO2 minus, NH3N, still protonated. Finally, what's going to happen next? We're going to pull the last proton off now from the amino group. Okay. And we're going to get the following. CO2 minus, CH, CH2, CO2 minus, and then H3, not H3, H2N. Okay, so it's a bit long there. So let's look and see what's going on. Let's look and see what's going on. Well, we've got 1, 2, 3 midpoints, and we've got 3 equivalence points. There are 3 ionizable groups, each of which is titrated in turn. And so it's going to look like this if we were to make a graph of pH versus OH minus added. It's going to look like this, where we have, 1 equivalence point, second equivalence point, a third equivalence point, like that. Okay, 1, 2, 3 equivalence points. It's called number 1, number 2, number 3, where we've titrated each of these 3 groups. Okay, ionizable groups. And okay, so what's happening here? Let's see how the charge changes first. It goes from +1 to 0. So +1 when we start, right? 0 at the first equivalence point, right? And then at the second equivalence point, we have, hold on. Yes, you got 2 minus charges and a plus. So that's -1, right? And then finally, at the third equivalence point, the charge is -2 because we have these 2 negative charges right? And no charge there. Right? So that's what's going on in terms of the charges. And actually that tells us about the pKa value, because remember, I'm sorry, the PI value, because remember, to find the PI, you have to average the pKa values on either side of the species that has no charge. And it's this one right here that has no charge. So we're gonna average this pK1, which is 1.88, right? And then the pKa for the carboxyl on the side chain, which is 3.65. And this one was 9.60. So you're going to average these two because they flank the species that has no charge. That's why we did the calculation the way we did. And so now there's sort of a little homework problem I'd like to give you. Calculate, okay, the PI of lysine. Now what you're going to have to do is you're going to have to do a similar kind of analysis by tracing how the charge changes as you titrate the amino acid. One more small topic and we'll be done. Okay. I want to talk a little bit about histidine and the side chain of histidine. So part E here. Finally, use the Henderson-Hasselbalch equation to determine the percent ionization of an amino acid side chain. Use the Henderson-Hasselbalch equation, okay, to determine, okay, the percent ionization of an amino acid's side chain in a peptide. Okay, and specifically here, we're going to use the example of histidine because it's one of the more interesting of the amino acids. So let's consider histidine. Okay, now in a peptide, the alpha carboxyl and alpha amino groups are tied up in forming what are called peptide bonds, and so they're not ionizable to a very great extent, except for the ones on the end, called the amino terminal group and the carboxyl terminal group. Those are charged. But amino acids in the middle there may or may not have an ionizable group as a side chain, or on their side chains. Histidine does. And so this is what it looks like. The side chain of histidine looks like this. Okay, it's called an imidazole ring, and it can be bear a positive charge. So for example, see the double bond here? That means there are 4 things around that nitrogen. This hydrogen bears a positive charge now. Okay, that's the imidazole ring. Of histidine. Okay, so it can lose that proton. Okay, or it can gain it back again. We can look at that too. So if it loses it, what does it look like then? Okay, it's lost this proton here. Okay, it's going to lose that proton. This is what it looks like. So it goes from having a +1 charge to having no charge when it's lost that proton. Yes, and the pKa for this ionization is about 6.0, and I want to emphasize that this is in a peptide, okay, not a protein, because in a protein, the microenvironment around the histidine side chain can tweak or change the pKa value. So it's often not 6, but here it is in a peptide which is exposed to solvent. And so we want to ask a couple of questions, okay? A couple of questions. One, what fraction of histidine side chain would be ionized in a peptide? What fraction, okay, of histidine's side chain would be, now I need to be careful with this term ionized. Ionized. I'm going to say unprotonated. Okay. In a peptide. I need to specify that because, again, in a protein, it's a different story. And let's look at two different pHs. Okay. At pH 7.0 and at pH 9.0. You look at these two different pHs. Okay. So at 7.0. Okay. So what we have to do is we have to use the Henderson-Hasselbalch equation. Okay. And we have to look at that ratio that I was talking about. Okay. So sort of looking at it like that. This is what the Henderson-Hasselbalch equation says. That the log of A minus over HA, okay, is equal to pH minus pKa. So this is just a rearrangement of the Henderson-Hasselbalch equation, which says pH is equal to pKa plus log of A minus over HA. This is just rearranging it slightly, okay? So plugging in a pH 7 for this side chain of histidine, what do we have? We have, and let's call this the ratio, okay? So the log of this ratio, okay, is equal to 7 minus 6, or 1. So the log of the ratio is 1. What does that mean? Therefore, the ratio is equal to 10, or 10 over 1. So what that means is that at pH 7, you have 10 times more of the side chain in its unprotonated compared to its protonated form. 10 times more in the unprotonated, which corresponds to A minus, over this protonated form, which corresponds to HA, okay? And so therefore, so it's about 90%, therefore, 90% is unprotonated. Okay. And this means actually unionized, because it is not an ion, whereas this other one is. So again, you have to be careful with that terminology. Okay, so or it's about 10% protonated, right? But 10% exists in that form on the left. Now, I want to do a little sidebar here, because I notice I use these approximately to find out how much it actually is unprotonated. Looks like I'm running out of ink here, folks. The actual, okay, percent that's unprotonated. Okay, this was just an estimate. Okay, actual amount is equal to 10 over 11 times 100, and that actually, folks, is 90.9%. Now, what did I do there? What did I do? Well, when percent is part of a whole, right? So it's 10 over 10 plus that 1 that's unprotonated. That's the whole. So it's 10 over 11. So you get 90.9, which is still about 90%, right? So that agrees with that pretty well. And as long as, yeah. So, but the less the less the distribution is skewed in one direction or the other, or in other words, the more you have approximately equal amounts, the more the percent protonated or unprotonated will deviate from the ratio. So and that's good to keep in mind. And finally now, very last calculation, let's calculate at 9.0, what percent is ionized. So at pH 9.0, what do we have? Well, the log of A minus concentration over HA, okay, is equal to, again, pH, pH minus pKa, okay. It's equal to 9.0 minus 6.0, or in other words, 3. And therefore the ratio itself, if that's the log, the ratio is equal to 1,000 to 1, okay? So that means that, what does this mean? Therefore, at pH 9 now, where you're 3 pH units above the pKa value, even more of it is unprotonated. The ratio is 1,000 to 1. And so therefore, about 99.9% is unprotonated, and only 0.1% is protonated. Okay, so that's it. That's how you can look at that. Yeah, the more the pH is different from the pKa, the more you have a skewed ratio. Okay, folks, that's it. That's it for this lecture, and I'll see you in class.